Today's video will demonstrate how to compute algorithmic efficiency. Hello, I'm James Helfrich. Efficiency is one of the most important metrics for determining the quality level of a given algorithm. The question is, what's the best way to compute efficiency? I mean, really, we could just compute by how much time it takes to complete the task, but that time depends upon many things, such as the speed of your processor, how much memory you have, other things that are running, and so on. A more deterministic way to determine efficiency is called algorithmic efficiency, and this is a function of how much the speed of the algorithm changes according to input size. This video will demonstrate how to compute algorithmic efficiency. We'll start with the definition. Algorithmic efficiency is how algorithm execution time is related to input size. And we have 6 basic measures. O sub 1, otherwise known as constant, means that the speed of the algorithm is independent of the size of the input. That's really the gold standard. Log n means logarithmic, which means performance is a log amount of the input in the algorithm. In other words, if we double the size of the input, it'll take 1 extra unit of time. O sub n is linear, which means performance is directly related to the amount of input to the algorithm. If we double the input, then it'll take twice as long. N log n is a combination of linear with logarithmic. N squared is performance's squared amount of input to the algorithm. So if we have twice as much input, it'll take 4 times as log. 2 to the n means performance is really, really bad. If I increase the input size by a single element, it'll take twice as long. Clearly, we want to avoid that. So let's take a look at a first example. Here we have a flowchart. We want to try to compute the algorithmic efficiency of this algorithm. Now, we're going to do this line by line, or in this case, flowchart element by flowchart element. We'll start with the decision diamond. Now, since the decision diamond is independent of input size, this will be O sub 1. And then we have the prompt and the processing. Now, once again, this can be performed exactly once, so it's independent of the size of the input. Now we have read file. Now, this is really going to depend. Is the file size of constant size or is it variable size? If it's constant size, we're O sub 1. But if the file size could change size significantly, then it'd be O sub n, where n is the number of elements in the file. Then we have these 2 decision diamonds here. Once again, there's no loops here, so it doesn't matter how big the input is, it'll still take the same amount of time to read the file. All things considered, this is O sub 1, unless the file size can vary. If it can vary, then it'd be O sub n. In other words, we take the highest order exponent of all the different lines to compute the algorithmic efficiency. All right, let's take a look at another example. This example is pseudocode. What we want to do is add a name into a sorted list. We got to find the right spot where the name goes and then insert it into the correct spot. So we'll start here, this line, and we're going to create a tuple with a minimum and maximum value, and this is performed exactly once. Now we have a while loop. Now, every time you have a loop, then think it's not going to be O sub 1. The question is, how many elements is this loop going to visit? And since this is doing a binary search, it's going to visit log n number of elements. Therefore, this is O sub log n. Now we have a return statement here. A return statement can be executed exactly once. So this is O sub 1. Now let's take a look at this if statement. By itself, this if statement is O sub 1. In other words, it's independent of the size of a list. Whether there's 1,000,000 elements or 2 elements, it's going to take the same amount of time. However, this if statement is inside a while loop, and the while loop is log n. Therefore, this is O sub 1 times log n, and that is O sub n. Observe that the same logic does not apply for the previous element, where we return out, because as soon as we hit that return statement, we exit the loop. Now we have a for loop. This is going to go from name size down to mid. Now, the question is, where is mid? If mid is at the end of the list, then it's going to be O sub 1. If it's the beginning of the list, it's going to be O sub n. But on average, it's going to be somewhere in the middle. And somewhere in the middle is O sub n divided by 2. Now, the interesting thing about algorithmic efficiency is we remove the constants. So O sub n divided by 2 is actually the same thing as O sub n. Now, the overall cost of the algorithm is O sub log n plus O sub n. With algorithmic efficiency calculations, the highest order exponent dominates the performance equation. And since we're using addition to add log n with n, then it's just going to become O sub n. All right, one final example. In this case, it's C++. We have a function called escape, and we're going to try to turn a lesson operator into an HTML entity of ampersand LT semicolon. Now, at the beginning, this is O sub 1, because we're not actually making a copy of text. If the parameter was passed by a value rather than passed by reference, then a copy of the string would be made, and it would be O sub n by itself. But since it's passed by reference, it's O sub 1. Now we're going to visit every element in the string. If there are n elements in a string, then we're going to visit it n times. Therefore, this is O sub n. The if statement by itself is going to be O sub 1. It takes exactly 1 unit of time to compare if a given character is a less than operator, but this if statement is going to be inside a for loop, which is O sub n. So therefore, this statement is also O sub n. Now, replace is a bit tricky here. It doesn't look like it's a loop, but we have to understand how replace works. Replace is going to take a given character and it's going to replace with something that's bigger, which means everything to the right of it needs to be pushed to the right. And that pushing to the right takes time. I have to shift everything to the right. So if I replace the element at the end, it's really not going to take very long. But if I replace the element at the beginning, then the entire string needs to be shifted. So this statement by itself is O sub n, but because it's in an O sub n loop, the overall efficiency is n squared. The overall cost is n squared because the highest order exponent of the function is n squared. So I have to choose between O sub 1, O sub n, O sub n, and O sub n squared. N sub n squared is bigger. Therefore, the overall algorithm is n squared. Now, the worst case scenario happens when the whole string is filled with less than operators, and that's going to realize the n squared. But notice if there's a constant or zero number of less than operators, the algorithm is actually going to be O sub n. This is example 3.1, 3.2, and 3.3 in the efficiency chapter of the software design textbook.